Building a small turbojet engine. Almost 2 years ago, I attempted to make a smaller version of my first turbojet engine using more common supplies, and it ended up not working at all. Recently, with the latest version of the Frankenjet engine cooling to 100,000 RPM and producing over 30 pounds of thrust, I was inspired to try again and looked to readily available turbomachinery. So after not much searching, I found several small turbo cartridges for less than $50. I got one of these and immediately took out the turbine wheel and compressor to measure and model a new housing for it. The goal of this project was to make a small and cheap turbojet that works and sustains on fuel alone, regardless of thrust. Learning from previous mistakes, I was not going to use any 3D printed parts and therefore had to find alternative manufacturing methods. Considering that the entire rotor and related parts could be obtained quite easily online, this left the stationary parts of the engine to be designed and put together. Breaking this engine down into 4 basic parts: the compressor housing, combustor, bearing tube, and turbine housing. It seemed simple enough and could be made in just 4 parts, but would require methods such as welding and lathe turning, which I did on the machine I built in a previous video. Now going into the actual build process, the stator could be made easily from small laser-cut vanes and welded to a bearing housing with a removable shroud. I wanted to keep the compressor side as simple as possible and use a mostly vaneless diffuser with a small number of vanes toward the perimeter to have the compressor shroud bolt through. The combustor liner was a simple annular design with significant bypass air at the turbine inlet in an attempt to keep things cool. Luckily, the turbine wheel shaft is exactly 8 mm, which meant common cageless ceramic bearings happened to fit. The journal bearings would have also worked, but not within the intended form factor. Oil also tends to be horrendously messy and guaranteed to leak everywhere, which I just didn't want to deal with in this project. After it was designed, I ordered the stator plates to be laser cut out of weldable steel. I stopped by my local metal supplier for the bearing tube and compressor shroud. These were bored out on my lathe and brought down to the final shape. The stator section was welded together and to the bearing tube. The bottom diffuser plate was also welded to the front end of the bearing tube. After welding, the entire core was cleaned up on the lathe to maintain concentricity and a tight taper fit to the outer case made of a stainless water bottle. The chamber is made from stainless sheet that had its hole pattern drilled before the inner and outer sections were rolled up and spot welded into place. The combustor can was then spot welded directly to the stator vanes, with a bypass gap around the inner and outer edges to reduce stator heating. A fuel hose was inserted and wrapped around the chamber head to deliver propane gas. The diffuser plate was tapped, and the aluminum vane spacers were glued into place for temporary fixturing. The case and compressor shroud were then bolted on, sealing up the inside of the engine. The bearings were inserted with a central spacer, preload spring, and bearing seal plate to keep debris out of all the ball races. The turbine shroud was last, with a welded flange allowing careful positioning with several machine screws. After some fiddling with bearing alignment and preload amount, I got a very low friction rotation shown by the extreme speed achieved from a cold spin-up. A spark plug was installed, and it was clamped to the test stand for a first test. Unfortunately, the first attempt did not go very well, with an underpowered blower and interference issues preventing startup, and a bearing failure finally ending the test. It didn't take much teardown to see that the tight shaft fit on the full ceramic rear bearing was not a good thing, and as soon as it had ignition, the slight thermal expansion of the shaft cracked the unforgiving ceramic. This is not good because that was a very expensive bearing, and I needed to come up with a different solution. Thankfully, the world of remote-controlled turbines had the answer: hybrid angular contact bearings that had steel races and a full complement of ceramic ball bearings. I also remachined the turbine shroud because expansion was again causing the blades to grow beyond the 0.2 mm tip clearance and collide with the housing. With these tweaks and it spinning smoothly with a better starter blower, it's time to try again. This time, the engine roared to life and continued spinning after the blower was removed. However, I noticed that it didn't spool out much past the initial level, and adding more fuel didn't help. It is only running at around 50,000 RPM, which is fast, but not that fast for something this small. The original turbo was rated for 280,000 RPM, meaning with a more efficient design, it could have an order of magnitude more power. Despite its comparatively low performance, the tiny turbojet's longevity was much better than similar attempts, with a combined runtime of more than 10 minutes, and no bearing or melting problems by the time the test was concluded. In terms of measured thrust, this little engine made only around 5 newtons, or about a pound, so thrust to weight was not good by any measure considering it weighs 2.5 pounds. The primary reason why it got such low performance was a combination of the simplistic vaneless diffuser, incomplete combustion, and a poorly performing NGV section. All of these shortcuts made it easier to manufacture or made it cheaper, but all came at the cost of performance, leading to the barely sustained operation. This is still hopeful because there's lots of room for improving this design with only minor tweaks. Using a high solidity welded vane diffuser would de-swirl the air out of the compressor and reduce compression losses significantly. The combustor really needs to be more open with more numerous holes that are scooped towards the oncoming air and also made as long as possible. Commercial turbojet combustors have a slightly higher hole density and chambers that are roughly twice as long as this design, so combustion has more time to complete before gas exits through the turbine. This incomplete combustion can be seen as small flames coming out the back where combusting gases are expelled before the reaction is finished. The nozzle guide vanes in this turbojet were typical of a radial inflow type, but with one critical flaw. The throat constriction was not just along the blade height, but extended down into the dead zone behind the turbine rotor, wasting exhaust gases and contributing to extra turbine heating. That's why the turbine was glowing a bright orange color instead of the typical dull red seen in previous, more efficient versions. In terms of project cost, this is my cheapest turbojet yet, totaling about $142 of required supplies. This makes it a pretty good budget build, but the metalworking tools needed still make it inaccessible to many. With the mentioned improvements, this build has the potential to produce around 100 newtons if everything is well tuned and idealized. Improvements to the diffuser and NGV would fit within the existing form factor, and a stretched chamber would give it the final boost to be a competitive microturbine. This would be difficult considering the very short turbo core, and it would require additional shaft modifications and rebalancing. This project has inspired more experimental turbine ideas and sets a very functional foundation for future iterations. I plan on making some of these improvements to see if I can unlock useful performance for such a budget build.
Piss off so many neighbors.
Yeah, this thing is a little too loud. It just screams. Well, it works though. Too loud. Nice.